So this is a tutorial session that was actually taken at one of the CC universities about a week and a half ago, and I'm just going to be repeating some of the information that we covered in that one today. The server opens on Monday, so I thought we should prepare with some new material, which this sort of is. So we'll just go through it. So there's been a few requests for me to do a tutorial based on input, user input in particular. So I thought that I would produce this essentially to be able to talk through a bit about input and different methods of interaction in a game world that we can use using the mouse and keyboard. That's the general focus of today's subject. So we're looking at input, as I said beforehand. So for that purpose, I've built like what we call a dual stick shooter. You may have heard of these. They used to be very common in arcades, where you would have two sticks. Essentially, one stick would be for movement, the other one would be for shooting. We'll be covering a few different input methods, but essentially we're looking at an overhead game where we can sort of walk around with some keys and we can shoot with other keys. That's the idea. So we'll be talking about that today. We'll be going through some other stuff as well, and you can see the character is moving towards the cursor there, and we'll be talking about how to make that happen and some other kinds of input too, which require a bit of thinking and a little bit of maths, but that's okay. We'll go through that and go from there. So, right, let's get to it. So, this should be in your upload, so you can just check the description of the video and it should be uploadable there, and you can just download it from there, just wherever you want to. If you followed the tutorial for Breakout that I did the other day, then this should look very similar to you, very similar code in the way that it's run. We've got a few new bits and pieces around here and there, but you should having trouble looking through it. I recommend having a quick read through now and having a go at it. Ignore the reticle for the second, we're not going to be covering that just now, but the other stuff is fairly basic. So, essentially, in the code, we should have this thing here called a handle input method, and this is where we're going to be looking at focusing most of our efforts today, because everything else is sort of done for us, so it's just going to be our input. Now, whenever we want to do input for a program, as I mentioned beforehand, usually we have input being done in tandem with display, so you often do the display first and you have an input come after that, and those two things usually make up the core of the game. And in this instance here, we usually handle all the different kinds of input that can occur. So the big ones that we're going to be looking at today are going to be key events, which is when you type on the keyboard. Then we're going to be looking at mouse clicks and mouse drags, which is then dragging the mouse and clicking various parts of the screen, and the mouse scroll, which is when we use the mouse wheel for different things as well. And they're all going to be looked at in different features and things as well. You can see at the bottom of the code here we have this thing ID is equal to timer. And this is the game timer. Again, we showed you this in the breakout tutorial the other day, and this should be of no surprise to you. So that should all be fairly simple as it goes. So let's start with the key events, because it seems like a fairly intelligent place to start. We'll look at sort of capturing keys. This is always a fairly tedious task, because you have to cover usually each key individually or in sequence, seeing as there's very few relationships between the individual keys on the keyboard. Because, yeah, so they're individual character codes. Now, this is not the same as a char event, which you might have heard of before, a char event, which will return the physical key that you type. So if you type T, it will return a character that represents T. Key events return key codes, and these key codes represent the keys that you typed on the keyboard. And that's a really important distinction to make, because it does modify the way that this sort of thing works. So if you're curious to how they work and want to learn a bit more about key events, what I recommend doing is we'll just go here and just edit something like this thing here, which I've just written here very quickly. It doesn't have to be anything fancy at all. This is just very basically, essentially accepts one parameter, which is what the key event does, and you can just print it here as well to show what the key code looks like. With regards to always.pull event, I should talk about this in a bit more detail, as it's important for the input. As I say, events, particularly input events, can have more than one kind of parameter, so it just depends on which ones you're going to be capturing, so which one to be using. In this instance here, the key event always returns two parameters. The first one is ID, which every single event returns, and that is a string representing its ID, which in this case is always just going to be key. And P1 here is the key code that you type in. So we'll look at some key codes and see what they look like. These, if you're curious, do correspond, I believe, to Unicode characters, so you can actually look those up online if you're curious about them in more detail. But you can see here, we'll just type some keys on the keyboard, and you'll see just some random numbers are appearing on the screen. Just to think about it, we can look at the arrow keys. So if we hit the up arrow key, we get 200. Hit the down arrow key, it's 208. The left is 203, and the right is 205. So we can essentially say, if key is equal to 200, then we've hit the up arrow key, and we can handle input for up as well as stuff like that. Enter, I believe, is 28, space is 57, left control is 29. So we can use a few of those different key codes and things like that as well. We'll probably be using the mouse button for shooting, or perhaps a space bar, so we can use that as one as well. However, as you can see, memorizing all those codes is kind of annoying. So Lua thankfully has something called the Keys API. And if you're curious, you can just go something like for KV in pairs keys do. Print K V, something like that. Yeah, and you can see this is going to give you a nice long list of every single key code that you have here as well. So you have things like U, T, W, and they have all these key codes listed here as well. You notice up, so the keys to up essentially is the up arrow key, because we figured that was 200 beforehand. Same with the right there as well. Yeah, period. So there's a few ones that you can look in there as well, which are easy to work with. So not too difficult in that regard. So let's go back into DualStick and let's start doing some stuff like that, because it's, as I say, we've seen it's not too difficult. All right, so incidentally, if you're looking for a key code and want to know what the keys dot thing is, you could probably just do a search doing the same for KV thing as I showed you beforehand, but yeah. Alright, so first off, let's get our character moving around. So I think it's usually traditional to use the WS, A, and D keys for these sorts of shooters to move the character, but you can use the arrow keys if you want to. So we're going to decide on that input there. So we're going to go if P1, you can see here that P1 is our first parameter. So if P1 is equal to keys dot up, then also if P1 is equal to keys dot down, then, and this is what key binding code usually looks like. It's long, and it's, yeah, a bit annoying to write, but yeah, it gets the job done. Alright, so that's it. You can do this in tables as well if you want to try and save yourself a bit of time, but I don't think it'll save us much time here, so we're not going to worry about it. Alright, so if keys dot up, then essentially we want a player to move upwards. We're not going to worry about binds too much, that's for another day. So we'll just look up here and see that we have player has an x and a y position, so we can just go player.y is equal to player.y minus 1. And yeah, you can see this is pretty much how it's going to work as well. And this is how input usually is handled. It's just a matter of just covering through a big sequence of cases and just sort of managing them individually. There are tricks you can use to try and sort of shorten it down. If you ever look at my MPaint Pro program, you can see this massive list of key bindings that I have to use. They don't change, but they should really be organized or something to make it a bit more attractive. Alright, but that should pretty much cover it. So we've just added some simple changes, so up and down, just -1 + 1, left, right, -1 + 1. This will be more detailed later, but for the second it's good enough, so let's just make sure that our character is moving around. One last thing I like to add as well is something like this. P1 is equal to keys.q, then running is equal to false, just so we can quit out of our application easier than we would otherwise. So now we should be able to walk around, and there we are. So our character is now moving nicely. If you hold down the keys, you'll see that he's going to move really quickly. Now, this is really important when we're looking at the way that keys work. So, with our key bindings, essentially, the key event will be struck each time the keyboard passes the event through to the computer. So, if you've ever held down like the T key, for example, in Microsoft Word or something like that, you will see usually that the first key will appear. That the very first T will appear quickly, and then after a break, the other T's will appear in sort of a quick succession. Sometimes you'll see them speed up as they do that. It depends very much on the environmental system and sometimes on your keyboard. In this instance here, I don't know what's controlling the speed, but essentially you can see it's really just, it just has one key slowly and then a bunch of keys very quickly. So you cannot capture the state of the keyboard. You can't tell what's up and what's down. That's not possible in ComputerCraft. So yeah, that's very important to recognize. All right, so we can hit Q there, which is nice, and then we can go back to DualStick and start figuring out shooting, which is not difficult. So we just need to, essentially we have this list of bullets here. They can be of 3 colors, orange, yellow, and green, and we have a select of bullets. We can just use bull types, cell bull, to decide what color our bullet is going to be. But besides that, our bullet really just has an X, a Y, an X step, and a Y step, which indicates its initial position and how fast it's moving each individual movements as well. I recommend that X step and Y step should be added up to equal 1. That way all bullets are traveling at roughly the same speed, and you can control their speed by controlling the refresh rate of the application. So that's something I recommend. So feel free to ignore that or pay attention to it as you see fit. It is a very good idea to keep these sorts of things normalized so you can work with them easier. But yeah, and you can see we have a create bullet method here, which just handles that for us. So it's just X, Y, X, Y, and Y, so very basic. So with our dual stick shooter, we know that we're going to use the up arrow keys. I think again it's up to you. You can use I, J, K, and L as another classic one, but I think I'm going to use the arrow keys. So let's keep going. So P1 is equal to keys dot up. It really helps to touch type to get these things done quickly, I must admit. Right, so let's handle our movements. So essentially we're going to be creating new bullets. So it's going to be create bullets. In this instance here, essentially we want to have the bullets one step above the player if possible. So I'd probably make it, so I'd probably go player.x, player.y, and then we're just going to go -1, and then his stepping, x step is going to be 0, and his y step is going to be equal to -1. And it's just a matter of just replicating that code for each of the 4 steps. So, let's do it. Looks good to me. I think that will probably do. The bullets will handle themselves automatically, they'll remove themselves, so they're being updated automatically. It's just a matter of creating them is the tricky bit. So let's go back to dual stick and let's move around. So now, we got arrow keys. What have I done? Yeah, I've minded twice. So I've used the up arrow keys here, whereas I should use WSA and D. So let's do that. Okay, so now we're walking with WSA and D keys, and we're shooting with our arrow keys. I'll have it die hard, I guess. And there we are. So we're seeing some nice bullets appearing. They're just firing off in the directions that we're shooting them. And you see they're all moving at a nice consistent pace because they're all both the x and y values always add up to 1, which is nice. So that's looking pretty good. That may seem like a silly thing to pick on now, but it'll matter later, I guarantee you. So, okay, that's looking pretty nice. So now we have our character moving around and shooting, and we're using input quite effectively. Let's have a go at using the mouse this time. Essentially, there are some shooters that you'll play. I can't think of any off the top of my head, but there are a lot of particularly older shooters where essentially you would be able to move around with the arrow keys, and you would shoot by clicking the mouse, and the character would then face towards the mouse and fire in that direction. So that way the bullet should pass through the mouse. And that seems like it's sort of a difficult thing to do, because if you think about it, you have to sort of know how fast does the bullet have to move in the X and the Y to be able to pass through the mouse? How do we keep that consistent with moving sort of there, or there, or there, or there? You know, and it sounds like a difficult problem, and it sort of is. But we'll go through it. So let's look at how to make our mouse the position that we're going to be shooting to. So let's look at the different things that the mouse can do first, because the mouse capturing events is a bit more complicated than keys. We'll use the scroll first, because the scroll is nice and easy, at least for our problem. We're going to use the scroll to select our kind of bullet. So I mentioned before that we have 3 kinds of bullet: orange bullets, green bullets, and I think pink bullets or something. I've already forgotten. Yellow bullets, right. And we have the cell ball thing here, which is equal to 1. So obviously if it's 1, then we create a bullet that's type 1. Otherwise create bullet that's type 2, create bullet type 3. Our create bullet code actually does that for us automatically. You'll see that that's being done for us. So it's just a matter of just updating that level whenever we want to change our bullet type. You could do that on the keyboard. In fact, there's a lot more you could do with the keyboard. You could even have diagonal shooting if you wanted to. We're not going to handle that right now, but you could. But yeah, we're going to use our mouse scrolling to handle capturing essentially those movements. You can see we already used the mouse scrolling for scrolling our window. So it's not too difficult. Essentially, mouse scroll returns 3 parameters, so P1, P2, and P3 are all filled up. So P1 is going to be, so the second parameter that OS deploy event returns when we return a mouse scroll is going to be the direction of the mouse scroll. So if we scroll upwards like that, it's going to be equal to -1. If we scroll downwards, it's going to be equal to 1. And that's always the way that it is, so it's either -1 or 1. P2 and P3 refer to the X and Y coordinates respectively. So if we, for example, here, it'll be 1, 1. For here, it's going to be W, H. So those will be passed through there as well. But like I say, we don't have to worry about that because where we're scrolling doesn't matter that much. Usually we're scrolling independent of position. We just want to change bullets. So in that case, it's just P1 that we're worried about. And that's really convenient because we want to increment by 1 or -1 depending on whether we're scrolling up or down. So that's really easy. So we can just go cell ball plus P1. And then, of course, to make sure we don't go out of bounds, if cell ball is less than 1, then cell ball is equal to, let's just go, I think it's bullet types, I think. Bull types. And then just else if cell ball is greater than. There are faster ways to do that, but this will do just for the fun for the second. You can compress that into one line, and it's always fun trying to compress your code. But all right, it's a good idea now just to give that a bit of a test, make sure that's working nicely. So we're just going to go dual stick again, and now when we scroll our mouse, you can see the bullet is changing down below. So you can just scroll there as much as you want to, and that'll just scroll through the bullets. And now when we shoot, they will then be the color that we specified. So there you go. That's working quite nicely. Again, if you're curious, you can always look at the code. That's all there. It's not going away. So, all right. So that's looking really good. Now let's actually get him so that we can shoot in the position we've got going there as well. And this seems like a tricky problem, and it sort of is, but we'll talk about it in a bit more detail. So we have our mouse click next, and the mouse click is what was going to be doing the shooting. So a mouse click is very similar to a mouse scroll. It has almost exactly the same parameters. It's a little bit different. So P1 refers to the mouse button that was pressed. I understand this goes as high as 3. I think it goes up to 5. It used to include the mouse wheel. I think that's been moved into the mouse scroll now. But certainly the left mouse button is going to be equal to 1, the right mouse button equal to 2, and the middle mouse button equal to 3. You can actually just have a go at pulling the event in another program and just testing to see what those buttons are if you have like a big button-y mouse. I'm not sure how many is captured, so that might be worth checking out. We'll just be looking at the ones, so P1 is a bit less important for us, but where you have mouse left and right clicking, that's really important to check between those two. And 2 and 3 are the same as they were beforehand. They're equal to X and Y, but this time they do matter, so we'll be looking at that directly. Let's think about the problem a bit first, and then we'll talk about actually how to fix it. It's just, so essentially, suppose that our character is, we'll make him that green dot that he was, and we'll put him sort of in the center here, and then we've just sort of clicked, and our mouse click is over, for example, sort of, I don't know, here-ish. Right, so what we want to do is we essentially want to be able to draw this sort of line to intercept, you know, where that bullet is going to sort of hit. A little black spot there, indicate that's there, and that way we sort of know, right, this is where the bullet needs to travel to, and if we can essentially get the idea for how fast it's moving in that direction, then we know that it's going to keep going the way that we want it to shoot. So essentially we do want to be able to draw a line between the bullet and the character and be able to figure out where that bullet's going. Now we don't have to define our bullets in terms of like a direction, like a rotation or anything like that. We define them in terms of their X step and their Y step, and we've used that beforehand, and that is important. So if we use rotation, it'd be different, and we'll talk about rotation later, but for the second, we do know that we use an X step and the Y step, so we need to calculate how far he's moving each step in the X direction and how far he's moving each step in the Y direction, like that. And we can already see from this, for example, here that this is going to be maybe a third of that, but it does make a difference to sort of check. So essentially, if we want to figure that out, we can be clever about it. So we do know that if we create a triangle, a right-angled triangle like this, we know that the distance between essentially that the bullet is going to have to travel. For example, if they were to travel one step, it would be this far in this direction, this far in this direction. Then it would immediately arrive at the destination. So these two directions are the length of these two lines here, which, if you think about it, is actually just going to be the movement on this position here minus their position there as well, and that will get you that essentially that point there. So yeah, if we consider this to be, I don't know, P1 and we call this P2, then P1.x, P2.x, then we know that the X step here is going to be P2 minus P1. I wish I could write that down somewhere, but I can't. That's a 1. So 2 minus 1, I'm sorry. So we have P2 minus P1, and then here it will be P2.x rather P2 minus 1, and then P2.y minus P1 dot y, and that will get us the X and the Y step there as well. Now you may think to yourself, well, that sounds kind of useless because that's a massive series of X's and Y's. How on earth can we use those to do anything useful? And the thing is that if we divide these distances down so that their lengths added together are equal to 1. That is to say, if we turn them out and we normalize those values, we'll get the smallest step that the bullet can make, and then we just need to add that step over and over again, and we'll eventually move in the direction that we want it to. That's the general principle that we're going to use behind getting this to work. So, yeah, it's a matter of like finding out how far it needs to move in the X and the Y, and then getting that down to a speed that is useful to us. So, again, as I mentioned beforehand, it's going to be fairly basic. So what we're going to do is we're going to find local x diff and y diff, and this is essentially the distance between the points. So the difference between the 2 points between the player and the area that was clicked. So that's going to be equal to. Now we know that you might know the distance is always final take initial. That's the way that we find the distance. It creates what we call a vector that points in that direction. So yeah, actually, it might be worth showing you guys that. If you imagine, essentially, a vector is like a line that has a directionality. That's all a vector is. We just use an arrow to describe those. If we have the player being sort of here-ish, and we have our bullets being sort of here-ish, then we can actually represent them as being vectors. And the first vector is this one here. That's a point that goes from the center of the, from the very top corner of the screen down. And then the second vector, which we'll make purple, is a shorter one. Sorry, is one that goes sort of a bit like that there as well. Now, if we take this vector and we essentially reverse this vector and add it to this other vector, so you can see the reverse of this vector is going to be sort of that direction, upwards like that, and we add that together, we're actually going to see that the resulting vector is going to look kind of like this. Cool, and that's the factor of vector addition that we use in determining where we're going to be facing. So yeah, it's a good thing that when we're looking at the direction we want to move in, it's always the position of the final point minus the point of the initial point, and that gets us that nice pointing vector there as well. You can try that on a piece of paper if you're curious. It is actually worth doing. So and that'll have better precision than paint will. All right, so let's give that one a try. So if we're going to take, so it's going to be, as we mentioned beforehand, the final take initials. So the final point is going to be P2 minus the initial point, which we know is going to be player.x. And then the other point, y diff, is going to be P3 minus player.y. That's going to get this difference there as well, which is looking good. Now that we have that, we know that this might be positive, this might be negative. It's actually, we don't know at this point. It depends on what was being clicked. And that negative value does matter because that's going to define what direction the bullet moves in. So that really is important to make sure we have that handled beforehand. Now, if we want to, essentially what we're going to call it, we're going to call it normalizing the values, which means we essentially make it so both these values, when added together, we want it to be so that x diff plus y diff is equal to 1. That's essentially what we want, and we want that to evaluate to true, essentially. So how do we do that? The easiest way is just to go to x diff plus y diff, and that gets us the full point, and then we can just divide each value by that value. So it takes us the sum, essentially. So we can just go, for example, local x step is equal to x diff divided by x diff plus y diff. So if you think about it, suppose that we've got a distance of sort of maybe, I don't know, 5, 5. So I'll just write this down somewhere. 5, 5. And so that's our distance, and we want to essentially decide how we can make this being its value as 1. So we can see just from common deduction that this will be 0.5, 0.5. That's clearly because when you add 0.5, 0.5 together, half and a half, that makes a whole, which is 1, and that's what we want to see. So what can we use mathematically to represent that? We can see that 5, 5 should, in fact, because if we add those two values together, we get 10. And then if we divide those values, 5 divided by 10, that gets us a half, which is 0.5. And you can try that for a few more values to make sure that that works correctly as well. So we can try, for example, 3, 7. You'll see that's still 5, 5, but you'll get a different thing now as well. So now I have to go 3 divided by 10. 3/10, so that's going to be decimal form, 3 divided by 10, it's going to be something small, 3/7 I think. But yeah, it's 3 on 10, if you like, and this would be 7 on 10, which of course is equal to a whole. And you can try that with a few other values as well if you're really curious, but essentially that method of adding those two together and then dividing by the result is the way that we essentially normalize a series of values, so we're going to be using that now. Alright, so that essentially will give us that point where they're equal to 1, and that way they'll move at a nice consistent speed, which is what this is all about if we've forgotten. So x diff plus y diff, which is here as well, I'm going to go local y step is equal to y diff divided by x diff plus y diff. Now, there's a problem. It might be hard to see at this point, but there's a fairly big problem with this bit of code. And the thing is that x diff and y diff can be positive or negative. Now, suppose we have this situation here. 5, negative 5. Here like that as well. Now we know that what we really want to see is 0.5, negative 0.5. That's what the value should be. Because if you think about it, this still evaluates to a 10 long, because if we add 5 to 5, even negative 5, it should be pointing that direction there as well. We have 5 and the negative, and so that should be equal to a distance of 10, so we'd have 0.5, 0.5, or however long the line tends to be. However, that's not going to work for our equation, because if we add those two values together, we're going to get 0, and so what we're going to get is 5 divided by 0, which is, is going to be a math error, which is no good at all. So this isn't going to work. And so what we're going to want here is, because the distance, even though it is negative in this point here, it's not a negative distance, it's just that it's in the negative direction. So if you want to get just the distance, we get what's called the absolute value. And this is something you'll see come up in maths occasionally. And it'll look, for example, like the absolute value of x would be equal to, it would essentially look like this, where you have just the single long lines on either side. And this means just the value, so this ignores the negative component. So this will mean, essentially, it will be equal to x or negative x if x is less than 0. So essentially that would then create, if we were to make the absolute values of our x and y, it would then be equal to abs of 5 plus abs of 5, negative 5, and that is still equal to 10 because the negative sign is removed. And that just evaluates into 5 plus 5, like that. That's what absolute value means, and we have that function. It's called math.abs. It's in the standard Lua library, so we're going to be using math.abs here, and that allows us to create a normalized value like that. So let's do that now. So this now has to become math.abs xdiff plus math.abs ydiff. Don't be tempted, or should I say fooled, into going math.abs xdiff plus ydiff, because that will still have a negative result. It would just mean the end result is positive, which may not be very useful at all. So it has to be those two things evaluated separately in there as well. And so we'll just do the same for the top here as well. Okay, good. We're doing a bit of maths reading. This is the easy stuff too, so hopefully you're not finding it too difficult. Or maybe you're finding it very boring, very easy. I don't know. I have no idea who's watching this. Okay, so we have the x step and the y step, and we already know the x and y position. We can just add the x step and the y step to decide what that position is, because if you think about it, as long as it's one distance away, it's not intersecting the place, that's a fairly good position for it to be. So we can go from there. So we can just now create bullets with player.x plus x step, player.y plus y step, and then x step, y step. Cool. Alright, that's pretty much what we need to worry about. So let's make sure that that's working alright. It might not be. Now we're going to go dual stick. Looks like it's working okay. And now I've just clicking on the screen, and what you'll see now is the bullet's actually moving towards the arrow, which is pretty cool. Now, you'll notice that it's not always perfect. In fact, often it'll go like a little bit to the side. There's a good example there, so the bullet's actually missed my mouse cursor there. Now, the reason for that is because if you think about it, when we're clicking in certain directions, we're now dividing by a fractional value, but pixels don't have fractional positions. A pixel is absolute, it's either 1 or 0. And what happens is whenever you try to draw to a fraction, Lua will always take math.floor, and that will be used to the position. So sometimes the bullets will appear a little bit to the left of your mouse cursor when you're shooting down, a little bit to the right when you're shooting up. Sorry, a little bit to the left when you're shooting up as well. So there you are. It's always more towards the negative rather. So a bit higher and a bit more to the left than it should be. So that's the general trend that you'll see with those. So it won't always be perfect, but it's pretty good, which is really good. So I mean, you can do your own rounding function if you want to make sure it's as perfect as possible, but really this is good enough. So, and now we're firing with the mouse really nice. Then you can change bullets and move like that, and you can sort of see this turning into a game, which is really cool. Not a great game, but yeah, you could turn this into like a corridor shooter or something if you want to be a bit clever about it. So yeah, there's a lot of stuff we could do with that. So it's looking good. But we're not quite done yet. There's one more big thing left to do, and this is the really tricky part. So if you've found this hard so far, this might be a bit tricky, but you can stick with me if you want to. And that's going to be looking at getting it. So essentially, our player is no longer focused on just shooting, but he's actually now going to start turning around and moving in directions. So beforehand, I showed you in the solution that this player is not moving up, down, left, and right according to his positions. He's actually turning left and right. And you can see that little cursor there is turning around the player in this nice circle. And then the player is walking towards it, which is pretty cool. Now, how do we do that? That's a bit trickier, because in this instance here, the player is not storing an X step and a Y step because they're turning around a central point. So what that actually means is we're storing a rotation, and that rotational value is what we're using to determine whether the player's moving left and right. So we figured out how to work in a step, but how do we work with a rotation value? How do we do that? And that's where things get a little bit trickier. So we're going to start looking at that sort of nowish, and see if we can figure out how to get our player to work in that regard, and more to the point, how to get bullets to shoot in that direction, which is really useful too. So we'll look at that. It's actually not too hard. It sounds very difficult, but it's not too bad. So essentially, let's think a bit about what we want our character to do. So we want him to let's go. So suppose that the character is in the center of this point here. This is obviously, as you can see, this is just a circle that's drawn perfectly with the pixels. The circle here is very elongated. For my cursor, I've actually used a series of ratios to get it to be more circular. I've forgotten what they are. You can find it in the reticle code. Yeah, so you can see here we've used the values on the X it's 8 and on the Y it's 6, and that gives us a fairly circular circle. So that's what we've used there, and we use those dampening values for later, but for the second it doesn't really matter. But yeah, suppose the player is essentially at the center of this circle, and then and that cursor that we showed beforehand, that green thing, can be any point on the circle. It can be there or there or there or wherever it is. Now that point is defined by the player's rotation. So the player's rotation starts at 0. And on this graph hand, we're going to say that 0 is, if we have a rotation of 0, then we're looking at this vector here. Essentially the player is facing in this direction, towards the positive on the X and nothing on the Y. But essentially the player can then have a facing that's going, for example, like that sort of thing towards the cursor, wherever that happens to be. So that could be there or wherever it is that the person is pointing, and that's the direction essentially that we want them to be pointing in. So the question is, what is the step for that direction? What is the X step and the Y step according to that position based on the rotation? And if you think about it, when our rotation increases, our rotation is going to be increasing in this direction. So it's going to be increasing as we go around like that. It's going to come full circle, 360 degrees there. So it's 90 degrees there, 180 degrees there, 270 degrees there. And there's a reason we've done this, and there's a very good reason, but it may seem a bit strange. But essentially, this is our rotational value in here. So whatever this value is here, we'll just call that theta for the second. That's usually the easiest thing to refer to rotational values as. Is just whatever that angle is in there. So at theta is equal to 0, the player is facing this direction here. At theta is equal to 90 degrees, it's facing that direction here. At 180 degrees, they're facing in this direction here. 270, we're facing in that direction there. And at any point in between, they can be facing somewhere else. Okay, so how on earth do we find where that point is beforehand? What we can recognize about this, which is really nice, is the fact that we still have our triangle. It's just that our triangle is now a little bit different. So beforehand, essentially, I showed you a triangle like this. So we had like a nice edge here, what we call a hypotenuse, and that triangle was defined because we knew its X and its Y positions. We knew the positions, the absolute positions of these two corners. What that essentially meant was that we knew the length of these two sides. That's what we knew by knowing these two values there as well. Now this is a different problem. We don't know the length of those two sides, but what we do know is we know two things. First off, we know that this line here is always equal to 1. The length of that line is always equal to 1. Why is that the case? Remember I mentioned beforehand that we like to keep nice normalized values. This is one really good reason to do that. Because if we keep them normalized, we know that that length, that distance that the bullet needs to travel is always equal to 1. Now don't get confused with the cursor. With the cursor it's much longer. You know it's equal to 6 and 8 respectively. So it's equal to, yeah, whatever the values of that are. But when we're looking at the step the bullet needs to make to move from one point to the next, we know that that line there that they need to move is always equal to 1. We know that for a fact. That's what we said beforehand to make this nice and easy for us. So we know that this is equal to 1, and we know what this angle is here. The angle that separates the value between this line here, which we'll call our long line or adjacent line, and this line here, which is our hypotenuse there as well. So we could have a triangle that looks like that there, which might have, you know, a much shorter sequence of lines like that. But we will always know that angle, be it sort of a large angle or a very small angle, and we'll always know that this line is equal to 1. Those are the two things that we know for sure. Alright, so now the question becomes, how do we find what that number is? And how do we find out what these two sides there as well? So you may be familiar, if you haven't covered this in school, usually if you're about year 9 you will have covered this, what we call trigonometric ratios. A trigonometric ratio was something that was developed a very long time ago, and that's essentially a very, very long list of numbers that essentially forms a function that tells us the ratio of distances, the ratio of lengths between sides and its sequence of angles. There are three of these. We're going to talk about two of them in particular. We'll come back to this picture in a minute. I'm just going to tell you what they are, and then we'll talk about what they mean and things. Yes. All right. So we're just going to go edit. I'm just going to call this simple. I don't know. All right. So the two ratios that we're going to be talking about today are sine and cos, or sine and cosine. So our sine function essentially is a sequence of ratios, and this is a sequence of numbers that are the ratio of the length of the opposite side by the length of the hypotenuse. Whereas our cosine, sine, is equal to the ratio of our adjacent side by our hypotenuse. So if you're trying to think about what this opposite and adjacent thing is, remember the triangle I showed you beforehand? Essentially what we do is sine and cosine are functions that we can take. They are a long list of values, but they print out things based on one thing that's inserted into them as a function, and that thing is theta. That is our angle. So the angle that we're looking at essentially is used to create a ratio between the sides that are next to it. And this gives us the length of those sides according to that angle. So for example, with our sine function, we know that the opposite side is going to, by the hypotenuse side, is going to be this thing here as well. So that's going to provide us with a number that represents that ratio there as well. So that might seem a little bit useless, but because we know that our ratio side, that our hypotenuse is always equal to 1, it means we're always divided by 1, so that means that what we're actually getting when we pass through that sine theta is the length of our opposite side. Same thing with our cosine. So when we pass through this, because we know our hypotenuse is equal to 1, we're passing through the adjacent side. And all we have to do then, we can just multiply it by however long we want our length to be, and we've done it. So yeah, it's a quite nice thing that we can look at there as well. If you're sort of looking at this and thinking, well, I don't understand how those ratios work and things, and how they work, just take a look at this here again. So let's just let's take a look at the circle again. And let's think about it. So let's just think about it, for example, in this situation here, where we've got this line here, and in this instance here, what do we know about the value of this point? Suppose this is where our angle is equal to 0. We know at this point that x is equal to 1, because it's facing in the 1 direction, and y is equal to 0. So when we look at that, we know, and just write this down, if you have like notepad or something like that as well, when theta is equal to 0, x is equal to 1, and y is equal to 1. So we'll just for your sake. So theta is equal to 0. We know that x is equal to 1 and y is equal to 0. What about when we're facing in this direction up like this? Alright, so in this case we know that x is equal to 0 because it's in the center, we know that, but y is equal to 1. We're now facing upwards. So when theta is equal to essentially 90 degrees, if you like, then we know that x is equal to 0 and y is equal to 1. I'll let you guys do this yourself for the other two, so you can go back and rewind the video and look at that circle again if you like. But we then should see that when theta is equal to 180 degrees, we know that x is equal to -1 and y is equal to 0. And theta is equal to 270 degrees, we know that x is equal to 0 and y is equal to -1. So the interesting thing is we should then get a smooth line, essentially, because if we go paint a circle again, we know that it means that the circle has a smoother transition here from x being equal to 1, then it has to sort of follow a slope as it gets faster and faster towards 0. So it goes fast and then it evens out again. Then it goes sort of faster and evens out again here towards -1, and it goes back towards 0 again. I've actually drawn this as a graph so you guys can see what that looks like. And here we are. So you might have seen this before. This might be a familiar thing. But this is essentially a map of the sine and cosine functions. So remember that when we start at 0, which is here, we know that this thing here is going to be equal to, if you got your notepad next to you, it should be equal to 1, right? And then as it goes towards this point, you're going to go slow down towards, and then we get up to this point here, where x is equal to 0. Then it go down again go to x is equal to -1, then we come back up to 0 again, and then we go back up to 1. So if you can imagine this as sort of following the circle around, we're actually sort of drawing this function, because this is what x appears as we go around in the circle. And you can see this is the same for the cosine function, which is over here as well. This is looking at the x position, and this one's looking at y. So y starts at 0, then it goes up towards 1, goes down towards 0, then down towards -1 again. And it makes that nice wave function that we have sort of drawing along here as well. And this essentially is how sine and cosine work. This is what sine and cosine are representing. They're representing the ratios of those two lengths of lines and things as we go around that circle. That lets us sort of find out what those values are. So if you've ever wondered how that works and what they do, that's sort of it. So yeah, that's essentially how that works. So yeah, hopefully that sort of has cleared that up in your head. But essentially now what we know, you might know this already, but what we now know is that the step is very easy to achieve. So what we're going to do is we're actually going to change this code a bit here as well. So when we use the A and D keys here, we're now going to be changing the player's rotation. So when we go up, A, it means we're rotating clockwise, so our rotation is going up. Plus, you can just go something like just perhaps a unit of rotation is sort of a smart idea. I might go with sort of 0.1 or something. It's important to recognize that the rotation and the sine functions and cosine functions in this program use radians, not degrees. So I've been showing you I've been using degrees in the previous example. I'll just explain to you what radians are very quickly. They're not hard at all if you're worried about the word. Essentially, because we know that these values here are to 0, 90, 120, 270. Essentially, in radians, where this is equal to 360 degrees, 360 degrees is equal to 2 pi, 2 multiplied by the number pi. So you might be familiar with the number pi. Pi is equal to the ratio of diameter of a circle to its circumference. So other way around, rather, circumference divided by diameter. So right, yeah, so the ratio between the length of the circle around itself and the length in between the two, so when you multiply that by when you divide that by 2, you get that ratio that you probably would have seen beforehand, where circumference is equal to 2 pi r, which means 2 times pi times the circumference. So yeah, that's what pi is, and 2 pi essentially is the number of rotations that make up a radians in a circle. So 2 pi is equal to 360 degrees, where pi is equal to 180 degrees and 0 is equal to 0, just as it is beforehand. So we measure angles in terms of ratios of pi. So if you want to translate from radians to degrees, it's just a matter of multiplying. So if we're going from radians to degrees, what we do is we just go, it's r multiplied by 180 divided by pi. Because as we know, it's 2 pi, so we just halve it, we just flip that around, and that should get us that value. So that's the way that we translate back and forth. So it's just easy enough to remember that just 2 pi is the value where the circle stops, and that's all we need for this bit here. So let's just stick with that for the second. We'll go back down to our code. Alright, so where we're rotating here, rotation is 0.1 is fine. So 2 pi is sort of 6.2-ish thereabouts. So is greater than math dot, I think it's math dot pi. Then you can just go player dot rotation. In fact, we don't even need to really do this because the pi function is infinite, so it doesn't really matter how big the rotation is. So actually, we don't need to worry about that at all. We're just going to stick that as it is. So. Cool. All right, so that's got that going nicely. So we've now got our rotation working well. So, and what we can do now is we can actually test that if you like. So we're just going to go to dual stick. Just try rotating A and D, and you'll see that cursor is now rotating around the player, which is exactly what we wanted to do. As you can see, it's all that nice ratio that I mentioned beforehand there as well. Actually, looks a bit off to me. No, it's fine. I don't know what's going on. Anyway, it's right, but this is still moving up and down. This isn't moving towards our cursor, but by now, hopefully, you'll know how to make it move towards the cursor, with all that stuff that I just explained rather quickly. So remember the step that we're moving towards, essentially we're moving that step, and that step is defined by the ratio of those distances between the x and the y. And the equation that we'll be looking at, this one is pretty easy. So that means that on any point in that circle, x comma y, we know it's going to be the ratios using the sine and cosine as well. So that's actually going to be equal to the cosine of theta and sine of theta. Remembering that cosine represents our x values and sine represents our y values there as well. That's the easy one we can go for there. So that's how it usually goes. Now, the only tricky thing to remember, and this is a bit of an issue, is the fact that remember that we used Cartesian coordinates beforehand. So in Cartesian coordinates, I think I might have said beforehand that this was the sine function, this was the cosine function. I may have that mixed around. Anyway, this is cosine and this is sine. So yes, as I mentioned beforehand, we may have this situation here where we have in a set of standard Cartesian coordinates, y is moving upwards. So we go positive up and negative down, whereas it's actually the opposite in ComputerCraft, because of course the origin is in the top left, and we go down to go to positive. So we actually have to reverse that value. So in this equation, it's actually going to be equal to cos of theta and negative sine of theta, and that gets us those nice values really easily. So with that done, let's head out our joystick and let's sort of finish this up. We're pretty much done. So, when we want to be able to move the player up here, we just replace these values here, so we're moving towards this thing here, so we're just going to say that essentially we're going to player.x is equal to player.x plus, now in this case the x is equal to the cosine, so it's going to be math.cos of its rotation, so it's just player rotation. And player.y is equal to player.y plus math.sine. Player.rotation. Don't forget to reverse the direction of that, so that is now negative. And now, if we're moving, as we're moving backwards, and moving backwards is just as simple as moving back to the step. Minus. And you should see, as we said beforehand, where the player is always moving, where the added up step, because if you add these two values together, sine and cosine at a point, and this is the other thing we want to recognize as well. Just checking it off again. Just take a look at this graph here as well. I mentioned before about normalizing the values, make sure you're always adding up to 1, so the player always moves by 1 and the bullet always moves by 1. If you follow this graph, no matter where you look, any point you check to, if you add those two numbers together, you'll always get 1. You can't find a point anywhere on the graph where that's not the case. Those values will always add up to 1, and you can just test it whenever you want to. Just pass through two values, you'll always get 1, which is a really nice thing about the function. So yeah, that way we're working with these one values. You can see why keeping the values normalized is so important, because that's actually a fundamental part of the mathematics that we're relying on to get it work correctly. So. Okay, that should be enough, so now we should be able to test that. So I'm just going to try walking around. You'll see now the player is actually moving directly towards the cursor, just as I mentioned before. So, there we go. That's good. 0.1 is a very slow rotation, I might use that next time, but yeah, you can see that that's working well when he's moving towards the top. So, as I mentioned, nothing shockingly difficult. It's just trying to get your head around what all those different things mean and be able to apply them usefully in your application. We're now going to start shooting towards the cursor very quickly, and this is going to be very much similar to beforehand, so we're going to actually assign a key for this. We use the spacebar for this one, so we don't read everything. So in this instance here, beforehand, we need to be able to assign the bullet a shooting position as well, and this is, yeah, this is easy, so just create bullet exactly as we've done beforehand. It's just going to be x-pos. So it's just player.x plus this x-pos rotation. That way we're shooting towards the area. So here, rotation. And then those player rotation x and y is exactly what we want. So it's just it may seem like that was a lot of hubbub for what's a very small end result, and it is, but it's really important that you guys understand how the mathematics in that works. Looks like I've got that backwards. I think I might have gone plus there, or I should have gone minus. Because if you don't really understand what all that mathematics means and how it's working and things, it's very hard to apply this doing things sort of more extensive. So it's really good to have a good fundamental understanding of how your trigonometry works and things. So, whoops. That good solid foundation, you can do some really cool stuff. So there we are. That's better. That's why it took, even though it took a very long time to explain that, it took a very, very short time to code it, just because it's good to have that understanding. And you can see the bolt's going towards that really nicely. Alright, listen, that will do, so we'll take it from there. I'll do another tutorial a little later this evening, but hopefully you found that one really useful. It's some more complicated stuff, so you might find that a bit tricky, or you might find it very easy. It really depends on your competency and your age, I imagine, in a lot of ways as well. So, alright, that will do. We'll talk about some more stuff next week, and some more interesting mathematics to come as well. So, alright, that'll do. Take it easy, guys.